functions for the IB course. To start off with, I think a really handy thing to know is basically a certain powers. So exponents is another word for powers. Okay, and we're thinking here, 2 cubed or x to the 2, or 1 on 3 to the x. We can just see that each of these situations has a power. Now what I'd like to do first is actually just generate a table of our powers, so we should recognize these ones here. So I'm just going to draw a table like this. Okay, and then across. Hopefully that's enough powers, but might need a bit more. Now in this table we're going to consider some powers. So the most common ones we consider is 2 to the x, 3 to the x, 4 to the x, 5 to the x, and 10 to the x. Now you can add to this table if you so wish. You can add in other ones. And then we're going to consider -2, -1, 0, 1, 2, and just going to add a few more things on here. 3, 4, and then with the 2s we want to go a little bit further. Okay, the next step is going to fill this one in. So 2 to the -2. 2 to the -2 is going to be something here, 1 on 2 squared, which is 4, right? And then this one here, 2 to the -1 is going to be 1 on 2, so it's going to be half. We can also say this is 0.5, one thing to note. Next one, anything to the power of 0 is 1, so we can put a 1 there. And then these ones here, 2 to the power of 1, 2 to the power of 2, 2 to the power of 3, and 2 to the power of 4. Now these all become 2, 4, 8, and 16. Now with the powers of 2, I do recommend getting to know a few more, up to 10. I personally, I think that's where you need to be. So 5, 6, 7, 8, 9, 10, and we're just going to add on to this just for the 2s. You don't have to know this for the other ones. Okay, so let's add to this table here. And let's go. So we've got, this is 32, 64, 128, 256, 512, and 1024. Okay, and this is how many kilobytes are in a megabyte or bytes in a kilobyte. So this number does appear a little bit in society, but going up to the power of 10, knowing all these number facts are very useful, like your times tables. Now let's go back and do our rest of these key ones here, and we're going to look at some decimal answers too. In red, I'm going to add 0.25 there. So that's an alarm bell. If you see 0.25, it could be 2 to the -2. All right, this one here is going to be 1 on 3 squared, which is equal to 1 on 9. This one here is going to be 1 on 3. This one here is just going to be 1. And then we've got 3 to the 1, 3 to the 2, 3 to the 3, 3 to the 4. So let's go. That's 3, 9, 27, and 81. And we can go one further. Sometimes they do get this one, 3 to the 5, which is 2, 4, 3. Okay, now that's not as important, that one, but it can pop its head up. Let's keep going. Let's do the 4s. So 4 to the -2, 4 to the -1, 4 to the 0, 4 to the 1, 4 to the 2, 4 to the 3, 4 to the 4. Oh, we can just go 4 to the 3 for this one. So we've got, this is 1 on 16, 1 on 4, 1, 4, 16, 64. Okay, let's do our 5s. So there's 5 to the -2, 5 to the -1, 5 to the 0, 5 to the 1, 5 to the 2, 5 to the 3. And I'll switch to green here to mix things up. 1 on 25, 1 on 5, 1, 5, 25, and 1, 2, 5. And let's go to the 10s. So 10 to the -2, 10 to the -1, 10 to the 0, 10 to the 1, 10 to the 2, 10 to the 3, and we can keep going with this. We can see the pattern here. So this is going to be 1 on 100, 1 on 10, 1, 10, 100, and 1,000. In red, I'm going to go through and just add a few more decimals. So we need to know this one's 0.5. This one's 0.333 recurring, doesn't come up as much as decimal form, but this one does. This is 0.25. So that can come up there. This one here, very important, is 0.2. And this one here is 0.1 and 0.01. So in decimal form, it can appear. So we also have to recognize those. So now we've got these down pat, we're going to look at the index rules. You may note we've been using some index rules already, in particular the -1 and just something to the power. So on the right-hand side, we're going to go through the index rules. So here we go. And it's always good practice if you see if you can actually get all the index rules out. And I'll pull this up here and change that. My writing here. NDEX, index rule, index laws, index rules. First one goes like this: a to the m times by a to the n is equal to the a to the m plus n. The second one is a to the m divided by a to the n is equal to a to the m take n. The next one we have is a to the anything to the 0 is going to be 1. The next one we've got is a to the m, the power of n is equal to a to the power of mn, or m times n. And let's fix that m and n up. Saying m and n is sort of hard. That's why the rapid shows m and m. Next one. Now this is just sort of extensions on that idea. A to the m over b to the n to the power of k is equal to a to the power of mk, and that's just multiplied, b to the power of nk. Another extension of this same idea, a to the m times b to the n all to the power of k is equal to a to the power of mk times by b to the power of nk. Now what we're going to do is we're just going to look at some examples of these just to help consolidate your understanding of these, and we'll just switch it around a bit. So x to the power of 3 times x to the power of 5 is going to be x to the power of 8. We're adding those indices together. This one might be 2 to the 8 divided by 2 to the 4 is equal to 2 to the 6. I like this example because a lot of people here try to put it 2. It's not 2 because they divide those. Next one, we could have x to the power of 0. It's always 1, even if it's a variable. We may have, let's consider another example, x cubed to the power of 4 is going to be x to the power of 12. This one here we may have 2 to the power of x on 3 to the power of x, all to the power of, let's say 2. This will become 2 to the power of 2x over 3 to the power of 2x. You're timesing both those indices by x. And another example, switch colors. Let's go x to the power of 4 times by y to the power of 5, all to the power of a half is equal to x to the power of 2 times y to the power of 5 on 2. Okay, so this is a fractional one there, and we're going to consider a few more things based on these. So you may see there's a fractional power there, we haven't considered that yet, and we'll look at these negative indices powers as well. So from my experience, the fractional and the negative power rules are the ones that students typically trip over the most. So that's why I've had a little break there, get some examples, we'll get into that now. First one we're going to look at is a to the power of negative n, which is equal to 1 on a to the n. Conversely, 1 on a to the negative n is equal to a to the n. Now, for this example here, you might have x to the power of negative 3. That's exactly the same as saying 1 to the x to the 3. You may also have something like this. 1 on, and let's go 2 to the negative x. We can also express this as 2 to the x. Do you see here how the base is, a base could be an unknown or a number, and the power could be a known or an unknown? These rules still hold here, and I think sometimes that's where there's some confusion over when we can use these rules. Okay, but we can see it's the same. Now, a typical rule of thumb is that some questions ask for positive indices. Personally, I'm not that frightened by negative indices. I prefer it in this form sometimes, but you have to be able to convert between them. So at the very end of a question, it might go express as a positive indice. So if you have a negative indice like this, you need to convert it, and same for this. The next ones are the fractional powers, which probably people find the hardest. So with that in mind, I'm actually going to go through a few examples first, and then we're going to generalize. So here's a list. We've got square root x is equal to x to the half. We've got cube root x is equal to x to the third, and quarter root x is equal to x to the fourth. The general rule for this one here is there's a hidden 2. We don't see it, but it's like a square root, so 2 sides. Cube root, 3 dimensions. Quarter root. So all these here, right, that power goes 1 on n. 3, 1 on 3. 4, 1 on 4. So with this in mind, we can generalize and we can say, if I have an nth root x, then I can express this as x is 1 on n. Right? It's a good one to know. Well, you should definitely know it. The last one we're going to look at is when we start combining all these rules, right? So you could have the nth root of x to the power of m, for instance. Now, all this happens is you can re-express this as x to the m all to the 1 on n. So all I'm doing is just making it a fractional index. I really like to get rid of that surd form and go straight to a fractional index. And then we can see through our the rule that was shown, where was it? Up here, we can just multiply these powers. So we've got our rule here, which I'll write underneath. Okay, x m on n. Now, it's really handy going between these as well. There's some classic questions they ask that's based on those. Okay, now let's do some examples. I could well have been asked, what is evaluate? I'm just trying to think of a number here. No, that's not a good one. We could go... sorry, I'm just thinking of one here. Okay, let's go 16, and this is going to be something like that, right? Now in this case here, we can express this as root 16 all cubed, which is 4 all cubed, right? So we basically take the square root out, and then 4 all cubed, we can see from our table over here, is going to be 64. So that's going to be 64. Okay, and that's just sort of a nice example that sort of combines those ideas. Okay, so we're going to move on to next is looking at some of these exponential functions, evaluating exponential equations, and simplifying exponential expressions as well. And I'll just see the time on this video. Maybe what I'll do is I'll leave this as an introductory video and move on to that in the next video.